Okay, we are talking about chapter 12, kinetics, and last time we got into our sort of different order reactions. So the three common ones that we talked about are first order, second order, and zero order, right? Now, each of these have a sort of integrated rate law, like natural log of A is equal to natural log of A naught minus KT 1 over A equals 1 over A naught plus a KT, and A equals A naught minus KT. They also have half-life equations and also certain graphs that are sort of associated with each of these orders. Remember that each of these guys can be rewritten in the form of a straight line, which is a linear relationship. And typically, if you graph the natural log of A versus time, it will give you a sort of straight line where the slope here will equal minus K. If you take 1 over A versus time here, also should give you a linear relationship in the positive direction where the slope will equal K in this case. And lastly, if you take your concentration versus time, again, it will give you a linear relationship with the negative sloping line where the slope would equal minus K. Remember that in this case here, this is sort of like your final concentration. That's kind of like your initial concentration. That is your rate constant. And T here is time. So these, again, the equations that we use to figure out as time changes, how concentration will change accordingly. Remember as well that the units of the rate constant are really important. And a lot of times, as I mentioned, they will not necessarily kind of tell you what order you're dealing with. But again, 1 over seconds or 1 over some unit of time is typically what you have for your first order. 1 over molar seconds is typically what you have for second order, and molarity over seconds, which is usually the same as the rate unit, is what you have for zero. So if they don't kind of tell you the order of the reaction you're dealing with, but do give you the value of the rate constant, and more importantly, give you the units, that will help you sort of choose, which one that you should sort of use in your calculation. We finished up talking about energy, I think, and temperature, and we saw some energy diagrams, some exothermic type diagrams like reactants to products, where we do have, again, that activation energy, which is the hill that the reactants has to climb to get to the other side. And obviously, our endothermic type of deal looks something like that, reactants to products. E of A. Remember, at the very top of the hill, that is what is sometimes referred to as the transition state. And that is, as we talked about, where we have the transition state complex. That is, again, this sort of species that is partially breaking bonds at this point, partially making bonds. So really sort of transitional sort of species, which does not hang around a really long time because of that, because it's kind of in limbo there, breaking and making sort of bonds. And will usually come down to the other side really quickly. Remember as well, this is sort of exothermic and endothermic because that's energy on this side. When we take the difference there, right, between the energy of our reactants and our products, that's our delta H. And in the case here of our exothermic, our products are higher in energy. I'm sorry, lower in energy than our reactants. So when we take products minus reactants, we will end up with a negative value. That is opposite of what's happening over here. The energy difference, again, between those two would be our delta H. In this case, for endothermic, our products are larger value than our reactants. So when we take products minus reactants, we end up with a positive value. We finished up talking about sort of the Arrhenius equation, which is the equation that looks at sort of the rate constant and the effect on temperature. And that is as we saw here, I think on this slide. Let's back it up here. I think that's where we left off. We have our natural log of K is equal to minus E of A over R, 1 over T plus the natural log of A. Once again, this is written in the form of a straight line. Y is equal to mx plus b. The graph that we're looking at is not from this equation, but it's actually more so this guy. And what we do see again, as we talked about to finish up there, we have a lower temperature. There's going to be sort of less energy, so we're going to have a smaller sort of rate constant. Again, at a higher temperature, we see a pretty big jump in sort of the value of the rate constant with that higher temperature. Remember that in order for a reaction to take place, basically two things has to happen. They have to sort of collide with each other in the correct sort of orientation, the molecules, and they have to have that sufficient amount of energy. So again, here by increasing the temperature, adding more energy to the system, that's going to create a greater kind of pool of molecules that will have enough energy to get up and over to the other side. The result of that is you typically will obviously have more products being formed because more reactants can get to the other side, and you'll have sort of a faster rate. And vice versa, obviously, if you sort of threw everything on ice, which is like removing energy from that system. So now ones that normally would have perhaps enough energy to get up and over the hill to the other side will now have a lot less energy. So you're going to have a smaller proportion of molecules that can get up and over the hill to the other side. That usually will slow down your reaction because, again, there's going to be less reactant molecules being able to kind of hike up over the hill to make products in that particular case. This is the graphical version of it, which we will see on the next slide. But while we're here, this is what we would typically graph is the natural log of K. And then that would be go on the Y. On the X would be 1 over the temperature here. And this is in Kelvin, by the way. And this will yield you a straight line, actually with a negative sloping line. And the slope here would equal minus E of A over R. So this is a very common way graphically that you can figure out the activation energy, which is what this guy is. You could also figure out A, which is the frequency factor, which is sort of like the proportion of molecules that have enough energy to get over to the other side. The activation energy, when you solve for it here, minus E of A over R is equal to the slope, will end up being a positive value, and it should. As you looked at each of those graphs, our activation energy is a positive hill in terms of energy climbing. And that's because this line here will give you a negative slope. That negative with this negative will turn your activation energy into a positive value. And it should be a positive value. Also, a reminder that the R value here is not the one that we use, again, in the ideal gas law, but it is the energy version of the gas constant. So it is the 8.314 version of it, joules per Kelvin per mole. Any questions on any of that there? Obviously, as well, if you wanted to figure out the frequency factor, that would equal the y-intercept in this case, right? So if you know the y-intercept from your graph, you could also figure out, again, the frequency factor. Any questions on that there? All right. So again, here's a typical sort of curve that you could get from that. As I mentioned before, the sort of A is the sort of fraction of reaction molecules that have enough energy to get to the other side. Increase in the temperature, as I mentioned, pretty much will allow a greater proportion of molecules really to do that, to get to the other side and get over that energy barrier. Thus, it will also, again, increase that rate. And that's what we see in this graph. This is basically a reaction at two different temperatures here. Temperature 2 is greater than temperature 1. And what we see is in terms of temperature 1, which is down here, that is as much molecules that will have enough energy basically to get to the other side. By increasing the temperature, what we see is actually this amount of molecules will now have really enough energy to get to the other side versus what we had at the lower temperature. So again, we can see that increasing in temperature allows those molecules to get over that energy barrier to get to the other side. All right, so that's what we talked about there. So let's take a look at an example and sort of how we could use this. So obviously, as I mentioned before, this version of the equation that we were looking at there, which was again on this page here, is really sort of a graphical version of this equation. We're going to see a version of this equation where it's more of a mathematical way of solving versus, say, a graphing type way. So again, this is typically the one that's used for graphing. Again, we're going to, on the y, put our natural log of k. And again, on the x, we're going to go 1 over temperature. So if you're given this type of table with a bunch of this information here where we have the temperature and we have the rate constant, you would need to go through all of these values here. And since it happens to actually be in Kelvin, all you really have to do is take 1 over the temperature value for all these things. Obviously, if the temperature is given to you in Celsius, you got to first convert it to Kelvin and then do 1 over to temperature to get it converted. Now for the K's here, we basically need to just take the natural log of all these K values. You would do a best fit sort of line, XY scatter type plot. A reminder that there might be some problems in the homework here for the chapter 12 that you're going to have to make up some graphs to sort of solve it is kind of the best way to do that. And if you do graph it and sort of get your best fit line or add your trend line, you get a graph that looks something like this. Again, we can see natural log of k on the y, 1 over our temperature on the x, and again, we get our negatively sloping line here. So in this case, we're looking to calculate the activation energy and also the frequency factor. And here again, the natural log of k is equal to minus e of a over r, 1 over t plus the natural log of a. And that is how we're going to use our equation here, which is our y is equal to mx plus b. So clearly in this case, that right there is our slope. So that is the first thing that we need really to figure out the activation energy. So minus e of a over r is equal to our slope, which in this case is negative 1.12 times 10 to the 4. That will equal minus e of a over r, which is 8.314 joules per Kelvin per mole. We're essentially going to multiply that to the other side. We also want to make sure we do not forget to also multiply the negative to the other side. Again, that's what's going to turn our activation energy into a positive number. So that is a 1.12 to the 4 times 8.314. That's going to get us here 93116.8. Units here are actually joules in this case, right? Coming from here, joules per mole, really. But that is in joules and not kilojoules. So usually activation energy is given in kilojoules. So maybe something like 93.1 kilojoules per mole there would be our activation energy. But remember that R's value is joules. And if you're using R, obviously that's what it's going to end up with. Any questions on there? Now we also, again, can find the frequency factor, which is A. And as we can see here, the natural log of A will equal our y-intercept. Coming from our equation there, our y-intercept is 26.8. That's going to give us the natural log of A is equal to 26.8. We're going to E both sides there. The E on the left there, we'll get rid of the natural log, and we'll do a little E of 26.8. That is going to give us a frequency factor of 4.36 times 10 to 11. Now, when we think about sort of the units of frequency factor and we sort of get it from a graph like this, they actually will end up being usually the same units that we have for the rate constant. So they'll actually end up being the same units for the rate constant, which in this case is -1 molarity and seconds. That is because technically this is the natural log of k, and when you take the natural log, you basically get rid of the units, but we just took the e of it, which brings the units back basically to k, and that's how we get back to basically the same units basically in that. So we took the inverse of the natural log. So when you kind of do the natural log of it, kind of gets rid of the units, but then by taking the E of it there to solve for the frequency factor, kind of brings it back to the same units as the rate constant. I would say again, usually the frequency factor is a larger number. Again, it is the proportion of molecules, right, that have enough energy to get to the other side. And remember, there's lots of molecules in whatever you have, right? You have a small volume of liquid, there's usually lots of molecules involved there, right? 1 mole of anything, 6.022 times 10 to the 23 molecules, right? So, if you have like a mole or something, that's a lot of molecules, but usually you will have a good amount of number, or a very large number for that value. Any questions on how to graphically determine this information? Again, I would say I probably would not have you graph it, but a graph may be given to you, and you may have to use that information, obviously, to solve for something like this. Any questions on that? Maybe we'll just go old school, get the graph paper out, graph things by hand. They used to do that. They used to make you do that in lab, actually. So that is the graphical version of this equation, but really, if you know basically 2 points along the line that you're graphing, you can use what is sometimes referred to as a 2-point version of the Arrhenius equation, which is more of a mathematical way of solving some of these questions that you may have. This is the natural log of K2 over K1. Those are 2 rate constants basically at 2 different temperatures. And that would be T1 and T2 here. These guys do need to be in Kelvin. And these are obviously the rate constants at 2 different temperatures. E of A is our activation energy. And R is still our gas constant, once again, still the one with energy, 8.314 joules per Kelvin per mole. So there is this version of the equation. I'll be honest with you, there's about 3 versions of this equation that you might come across. Some people will distribute out the negative there in the parentheses where the temperature is and flip things around. Some people will combine the denominator there, T1 times T2. So if you look around, you may see a few different versions of this particular equation. If you find a legitimate version, they all will work the same. But this is one I'm going to roll with, which again is the natural log of K2 over K1. Here you do want to divide the rate constants before you take the natural log of it. E of A overall. E of A over R, that is the area where a lot of people really screw up a lot in this problem, which is right here in terms of units. Now, as I mentioned before, very commonly activation energy is given to you in kilojoules, and obviously R is here in joules. So very common in problems, you have like a factor of 1,000 difference there between them. It does require you to do some type of conversion, either convert the joules to kilojoules or to the kilojoules to joules. Whichever way you want to do it really will work the same. The other very common error that people make here is they leave things in degrees Celsius. Yeah, so again, needs to be in Kelvin, and that is a very common sort of thing. And sometimes people will do that because in the question, they'll ask you, what is the, say, temperature in degrees Celsius, and they'll give you the temperature in degrees Celsius. So people think they can leave it as sort of in degrees Celsius, but you do need to convert it into Kelvin to use this equation. All right. So why don't you try one here? Reaction here, we got a rate constant of 2.57 at 701 and 567 at 895. Find the activation energy here. Okay, so let's take a look, see how you're doing. So obviously here, we're going to use our natural log K2, K1 equals E of A over R, 1 over T1 minus 1 over T2. In this case, we have a K1 of 2.57. We have a T1. It's actually already in Kelvin, so we don't need to do anything with that. So that's good. We have a K2, 567, and a T2 of 895, also in Kelvin. By the way, it really doesn't necessarily matter which one you call ones or twos, as long as you keep obviously the K and temperature values together that go together. In this case, we are looking for E of A here. We always have R, which is our gas constant. So we got a natural log of our K2, which is 567 divided by 2.57 equals our E of A over our R 8.314 joules per Kelvin per mole. 1 over our T1, which is 701 Kelvin, minus 1 over our 895 Kelvin here. All right, so I'm going to kind of clean up the left-hand side there. So we're going to go 567 divided by 2.57. Then we're going to take a little natural log action of it there. And that's going to give me something like 5.396453 equals, and I'm going to also then multiply the 8.314 to the other side. And I'm also going to clean up what's in the parentheses as well. So I got 1 divided by 701 minus 1 divided by 895. That will give me inside here 0.000309215. Once again, going to multiply by that and then come back and divide by what's in the parentheses. So we will take our 5.39 and times it by 8.314, and that gives us like 44.866. We're then going to divide it by our 0.000309 number, and that will get us here an activation energy of about 145,096. The units here are going to be joules based off of the, really joules per mole, based off of the units from our R value there. We could divide it by 1,000, and that's roughly 145 kilojoules per mole, which again, activation energy is usually given in kilojoules. Any questions on that there? Again, here we got a positive number, which you should really get for activation energy. It should, again, be a positive value of energy. Any questions on that one there? All right, let's take a look at another one. Yeah. Actually, I'm going to change that one maybe. Let's see this one. What is the, let's see. Some numbers, I think. If the rate constant is go with 245 reciprocal seconds at 37 degrees Celsius, what would be the rate constant at 27 degrees Celsius if the activation energy is 45.6 kilojoules per mole? I'll do it as well since I made it up. Hopefully end up with the same number. Okay, let's take a look and see. So again, here we'll go with our equation. And like I said, you really can number these any way you want. So I'll just go with the order as it is in the actual problem. So I'll call K1 here 245. We'll go with a T1 that's 37 degrees Celsius. Here, K2 is going to be what we're looking for, actually. And T2 would be 27 degrees Celsius. And we have E of A, which is 45.6 kilojoules here. All right, so we do need to do a couple things here. We know we do need to end up with Kelvin there on our temperatures, so we got to convert that into Kelvin. So we're going to add a 273 basically to both of these guys here. And that's going to give us a 310 Kelvin, I believe, and a 300 Kelvin in this particular case. All right, so we can go in here, natural log of K2, which is what we're looking for, 245 equals here 45.6 times 1,000. And again, the reason I multiplied it by 1,000 is it will convert it to joules for me. And that's going to work well with the joules I have down on the bottom. Again, you do need to do some type of conversion, either make them both joules like I just did, or obviously you need to make the R value into kilojoules to balance out the units. I'm going to go 1 over my T1, which is 310 minus 1 over 300 in this case. I could clean up everything on the right-hand side here. 45.6 times 1,000 divided by 8.314 times 1 divided by 310 minus 1 divided by 300 here. That's going to give me on the right-hand side negative 0.5897555329. I'm going to E both sides here, and that will get rid of the natural log on the left. So K2 245 equals 0.554462929. Obviously, I'm going to multiply that over, and that will give me a K2 of about $1.36, we'll call it. It will have the same units as the other rate constant, obviously, in this case. Questions on that there? By the way, earlier we talked about that in general, if you increase the temperature of a reaction or a lot of reactions by 10 degrees Celsius, you typically will see a doubling of the rate. In this case, we actually did the opposite. We lowered the temperature by about 10 degrees Celsius, which means technically speaking, we should see the rate drop by like about a half in a lot of cases. So if you take 136 times it by 2, that's 272. Our original rate constant was 245. So it's about half-ish less than what it started at. And that's typically, again, what you can kind of see in this case. Any questions on the 2-point version here of the equation? All right. Extra example if you'd like to do it, but that's basically what we just talked about. All right, so let's talk about the final thing here in the kinetics chapter, which is reaction mechanisms and sort of what they are. So as you may know through a couple of things since you've learned in the past, not all reactions actually take place in sort of a one-step process where, for example, these reactants go and form these products. Sometimes these reactions do occur in multiple steps. So for example, you could have A plus B goes to C plus D, then like C plus D makes E plus F. When you add these reactions together, anything that's on opposite sides of the arrow that's the same will cancel out or reduce down. So in this case, C would cancel and D would cancel. Everybody on the left-hand side of the arrow stays there. Everybody on the right-hand side of the arrow stays there. And that gives us our overall reaction that we were looking for. So a lot of reactions do take place in these sort of multiple step processes or stepwise sort of fashion. And these series of individual reactions that lead to sort of the overall reaction you're looking for, these are what are referred to as elementary steps or elementary reactions. Now, for example, if we look at this reaction here, a little 2NO plus O2 makes NO2 in this case. During the process of this reaction, N2O2 is actually detected. Now, when you look at the overall reaction of what's going on, you do not see that listed anywhere in the actual reaction. What that would imply is that the N2O2 would have to have been made early on and then kind of completely used up in the reaction when it was all said and done. And that's where sort of a possible mechanism comes into play. So reaction mechanisms are essentially a possible explanation for how this reaction actually takes place, the different steps that are involved for how this reaction takes place. It doesn't necessarily mean, as we'll talk about, that every single time it kind of takes that pathway to get there. But this could be a possible way that the reaction really sort of occurs. So, for example, what they proposed here was first a couple of NOs get together and actually forms the N2O2 in the very first step. That is would account for why it is detected when this reaction takes place. But then in the next step, it combines with some oxygen to form our product here. And that would also account for why you do not see it in the overall reaction when it's all said and done. That is what we refer to something that gets completely sort of canceled out, gets made early on and gets used up in the reaction. That is what is known as an intermediate. So this is the possible or plausible mechanism by which this reaction will take place. Any questions on that? Now, as I mentioned before, a really important aspect of an intermediate is basically the definition of it, which is it does get made early on in the reaction mechanism. But the key thing for something to be an intermediate is it does need to get completely used up by the time the reaction is over, which means you really should never see an intermediate in the overall reaction of what's happening. If you do see it, then it's really not an intermediate. So an intermediate cannot be found in the overall reaction, but can be found in the mechanism that leads up to that overall reaction. So in this case, like I said, that N2O2 would be our intermediate. There's also something referred to as the molecularity of a reaction. Some reactions are unimolecular, which means that basically they only have one molecule that's reacting in the elementary step. Some are bimolecular, which means there are two reactions or two molecules reacting. And some are termolecular, which means there's three. Like we've talked about previously in a lot of reactions, right? You typically don't see very much more than like three things reacting at once. Again, you don't really see like 4, 5, 6 things sort of reacting at once. So these are very common sort of molecularities of these elementary steps. Probably 1 and 2 is very, very common. In the case above here, both of these would be considered bimolecular. Both of those elementary steps have two things reacting on the reactant side. So they both would be considered bimolecular. Now, one of the special things, I guess, is how you could word it, I suppose. One of the things that you are sort of allowed to do when you are dealing with reaction mechanisms and writing rate laws is something that we normally are not allowed to do in kinetics, which is we actually can use for any elementary step, we can use the coefficient as the orders. So if you remember earlier on, the only way we can figure out the orders is to use the experimental information to do so. So this is the one place where you can write a rate law for an elementary step in a mechanism, and you could use the coefficient as the order. So for example, here, obviously the coefficient here is 1. So the rate law you could write for this guy would be the rate is equal to K times concentration of A. Each of these guys have a coefficient of 1, which means you could write a rate law for this step that the rate is equal to K times A times B. That's A plus A, which is really 2A. So that we could use as the order, and we could write the rate law for that elementary step as the rate is equal to K times A squared. So this is really the only place where that is sort of allowed when you're dealing with mechanism elementary steps. You can use the coefficients as those orders. Again, if it's like what we were doing previously, you need to use the tabled information to figure out the orders. Now, how do we know if a mechanism is a good mechanism or a plausible mechanism? or a bad mechanism for that matter of fact. So that is what a lot of mechanism problems, as we will see, sort of will ask you. They will ask you like, hey, is this like possible way that this reaction takes place? Is this mechanism possibly the right type of mechanism? So there's really two main things that you have to look at when you look at a mechanism to determine whether or not the mechanism is plausible or possibly correct. The first one's pretty straightforward, which is when you take all the individual steps and you add all those reactions together, it needs to equal the overall reaction. So if you take all the individual steps and it equals the overall reaction you're looking at, like I did there where I went A plus B goes to C plus D and C plus D goes to E plus F. When I added those together, I got the A plus B went to E plus F. Then you're good so far. Obviously, if you add up all the steps and it doesn't equal the reaction you're looking for, then that's probably not a great mechanism. The second thing, which is really important, is the rate determining step, which is sometimes abbreviated RDS, rate determining step, should have the exact same rate law as the one that was found experimentally. So when you look at a mechanism and there is a step that has a rate law that matches the one that was found experimentally, then you know that that is the rate determining step. Or the rate determining step should have the exact same one that is found experimentally in terms of the rate law. What is the rate determining step? The rate determining step is the slowest step in the mechanism. It is the step in the mechanism that essentially is the one that determines how fast or how slow this reaction will take place. Hence the turtle, I think. It's kind of like when you're in the 15 items or less and the guy in front of you's got like 100 items. He's your rate determining step from getting out of that line, right? You got to wait for him to finish before you can get there. So the slowest step in the mechanism, that is usually the rate determining step, and that one should always have the same rate law as the one that's found experimentally. So very commonly in a lot of mechanism problems, not all, but in a lot of mechanism problems, they will actually say somewhere in there, hey, the observed rate law is this, or the experimental rate law for this reaction is this, and they'll actually give you sort of that experimental value. And then you have to kind of do it. Some mechanism problems, as we'll talk about, are kind of like proofs in a sense, like you know what the right answer is, but you got to prove that it's right type of thing. And that's some types of mechanism problems. So let's take a look at one here. So why don't you try here? What is the overall reaction? What in this case is the intermediate? And what can you say about the rates of step 1 versus step 2 based on the information that's given to you? The experimental rate law is the rates equal to K times NO2 squared. And it hopefully happens through these two steps. So take a moment and see which answers you can get. Okay, so let's take a look. We'll start with the overall reaction, which again, simply we just get by adding all the individual steps here, these elementary steps. So in this case, anything on opposite sides of the arrow can cancel or reduce down. So that and that should cancel. We could get rid of that as well, I think. And that looks like it. That will leave us an overall reaction of NO2 plus CO goes to NO plus CO2 again. Everything on the left stays on the left and everything on the right stays on the right. Any questions on that there? The intermediate in this case is NO2, NO3. Are they both right? Actually, this one is not an intermediate because it is still in the overall reaction, right? So remember that the intermediate has to be something that is made early on in the mechanism and completely used up by the end of the reaction. It should not be found in the overall reaction. So although we did reduce down NO2 in this case, it is still around at the end of the reaction, which means it's not an intermediate. In this case, it is only, in this case, the NO3 that completely cancels out. question on that there. Now, because this is elementary steps in this mechanism, we could write rate laws for each of these. By the way, they also gave us an important piece of information, which is the rate is equal to K NO2 squared, and that's like the experimentally found rate law, basically. So if I write the rate law for my very first step here, the rate would equal K, remember it's just reactants here, and that's really 2NO2, which will give me NO2 squared, and that would be the rate law for step number 1. For step number 2, we could also write a rate law for this guy. Also going to be the rate is equal to our reactant, so K times NO3 and CO, right? First off, any questions? I got the rate laws, reading those. Again, this is the one place where we can use the coefficients as the orders. Now, earlier we talked about that the rate law for the rate determining step should match the rate law that is found experimentally. Which step here matches the rate law that's found experimentally? Step number 1, right? Step number 1 has the identical rate law to the one that was found experimentally. Because this one matches the experimentally found rate law, that will tell us that step number 1 is our rate determining step. That is the slow step in the mechanism. So what that would tell us is, again, step 1 is our slow step, our rate determining step. And step 2 then should be faster than that, right? It should be faster, obviously, than step number 1. Any questions on that there? So in this particular proposed mechanism, it is that first step that really overall sort of determines how fast this reaction is going to take place. Any questions on that type of mechanism problem? So this is one type of mechanism problem where, again, you can use the information to figure out overall reaction, intermediates, and which one is sort of your slow step. Now, let's take a look perhaps at another type of mechanism problem, one such as this, where we have this reaction and we have an experimentally found rate law of K is times H2 NO squared. So in this particular proposed mechanism and question, they do not tell us necessarily which one is the rate determining step. So there is a really difficult way to determine which one is your rate determining step. And the rate determining step should be which step, the fast or the slow one? Yeah, so that's how you find it, right? In this type of mechanism, that would be your rate determining step. It is the one that's listed as a slow step. So that's a very common sort of mechanism type problem. They will give you a bunch of steps, and one of them will be listed as like slow, and the other ones a lot of times will be listed as fast. So the one listed as slow is your rate determining step. So what that means is if we're looking at this mechanism, if we want to know if it's kind of like a good or bad mechanism, the two things that we need to make sure of is when we add up all the steps, it equals this overall reaction. So we'll start with that. So we're going to take all 3 of these steps in this case, and we're going to add them together. Once again, anything on opposite sides of the arrow will cancel. So in this case here, I got N2O2 on opposite sides, so they cancel. I have N2O over here, so they cancel. And I believe that is all that's going to cancel in this case. That will give me, if I keep everything on the left-hand side there, 2NO plus H2 and H2, which is 2 of them. So one there and one there, basically. And on the other side of the arrow, I have 2 waters, one there, one there. and an N2. So does the overall reaction add up? It does, right? It matches the one that was given to us as the overall reaction, which is here. So that does add up. So we're good in that sense. By the way, the intermediates in this case are what things? Intermediate is N2O2, and in this case, also N2O, right? None of those appear in the overall reaction. So in this case, we actually do have two intermediates that completely canceled out along the way. Any questions on that there? So what we know is that if this is going to be I'm gonna clean up some of the stuff I scribbled here. If this is going to be a good mechanism, the rate determining step or the slow step should have the exact same rate law as the one that was found experimentally. So we could go to the slow step and we could write the rate law. And for the slow step, it would be the rate is equal to our reactants, which would be K times H2 and N2O2, right? And then we can compare these two to see if they match. Do they match? So you say no, and then you would say that this is a bad mechanism, right? The problem is you cannot actually compare them because you're not comparing, what's that old saying, apples to apples, right? The problem with the rate law that we have in the slow step is in that rate law in the slow step, we have this guy, right? That guy is a intermediate, right? So we cannot compare a rate law that has an intermediate in it to a rate law that doesn't have an intermediate in it, right? To know if it actually matches or not. So at this point, we really can't figure out whether or not this rate law does match. So what we need to do is find a way to get rid of or substitute out our intermediate for something else. So to do that, we go back to our mechanism here, and we can see that actually in step number 1, I see N2O2. It's really not in any other step. So I could actually use that to substitute out the N2O2, and then I could kind of look at it and compare again. We also see something that is different. It is actually, here is the arrows. It is heading in both directions, which means this thing will reach equilibrium. And basically what that means is the rate of the forward direction will equal the rate of the reverse direction. And because this is a reversible reaction, you have a forward direction heading to the products, and you have a reverse direction heading to the reactants. It goes in both directions. What that actually means for the rate laws for that step is you could actually write two rate laws. One for the forward direction, going from reactants to products, and you could write a rate law that is going from the products back to the reactants, where the products in that case would be actually your reactants. So if we write the rate law for the forward direction, I'll put an F, that is going from reactants to products, we would get a rate law that K is equal to NO, and we would square it, again, heading in this direction. If we write a rate law for the reverse direction, which is heading in this direction, that means that the rate of the reverse reaction will equal K times the concentration of N2O2. First off, any questions on how I got that? That is all from step 1 in the mechanism. Basically, both of those rate laws can be achieved from that first step. Any questions on that? So when this reaches equilibrium, as I mentioned before, these two numbers, right, will equal each other, which means essentially these two numbers are equal to each other. Yeah. That means that you could actually set the other part of it equal to each other as well. So you could actually set that the KNO2 or NO squared is equal to K times N2O2. Yeah. And again, because this value here and this value here are basically the same number, although we don't know what it is, but they are the same number, so you could set them equal to each other. Any questions on that? Once again, here we actually want to get rid of in our original rate law this guy, which means we need to isolate this guy by itself. So in this case, we're just going to be dividing the k to the other side. And that will give us that N2O2 equals k times NO squared divided by k. If you want to use the little numbers, basically it'll be k1 and k minus 1. Right? That means we now have something that we can take, which is all this, and substitute it into our original rate law. So that is what I'm going to do now, is take all that and substitute that into our original rate law. And if I do that, I will now end up with, I'll just try to write everything the way it is. We'll go with KH2. Then I'm going to have K NO squared divided by K. If I just kind of substitute that in there, right? All those Ks, right? There are all rate constants, which means should they be the same or different numbers? They are the same. Who cares what it is at this point, but they should be the same number. That means that really the K on top, one of them, and the K on the bottom should cancel out because they are the same numbers. That means that if we reduce that now down to the rate is equal to K H2 NO squared, that is now the rate law for our rate determining step that does not have the intermediate in it. Now we could compare this rate law without the intermediate to the one found experimentally. Do they match now? They actually do match now, right? And that is why we can't do the comparison like everybody wanted to do at the very beginning, because we have that intermediate in there. In the reality, it actually does match, which means this would be a good mechanism or a plausible mechanism, and is sometimes referred to as a way that this reaction could happen. Now, clearly, if we went through these steps and we ended up with a rate law that did not match the one that was found experimentally, then that would not be a good mechanism or a plausible mechanism for this reaction to take place. So this is another type of mechanism type problem where you got to do a little substituting out, a little bit of math to, again, sort of get two rate laws that really don't have any intermediates in it so that you can't compare it. Any questions on that there? Oh, what's that one? Why don't you try this one here? Show that this mechanism for this reaction matches the observed rate law. The two that's up here obviously should be the two over. Okay, so let's take a look since we're getting to the end here. So remember, basically two things need to happen for it to be good or plausible. We need to add up the steps, so we'll do that here. It looks like the O cancels, and that leaves me on the left here 203, and on the right 302, so that is good. We also see that the intermediate here is O, and we know that the slow step is our rate determining step, which once again should have a rate law that matches the experimental one if it is good. We could write it here. The rate is equal to K times O3 and our O. Once again, in this situation, we really can't directly compare that because we still have sort of that intermediate there in the rate law. So much like the previous one, we need to go to kind of, in this case, really our only option, the other step here to substitute out for it. Again, this is a reversible reaction, which means we could write two rate laws for it. The rate law of the forward direction going from reactants to products would be K times O3. Going in the opposite direction or the reverse direction, the rate law in the reverse direction would be K times O2 and O. Once again, because these numbers, when it reaches equilibrium, will equal each other, we then can set both of these guys back equal to each other as well. And that would give us KO3 is equal to KO2 and O. Remember, again, we want to get O by itself. So we're going to take both of these guys and divide it to the other side. That will give us O is equal to KO3 and KO2. That right there is what we're going to substitute into for the O. That will give us the rate is equal to KO2. And now substituting in what we got there on the bottom. Once again, two of these rate constants will cancel out. That will achieve us the rate is equal to KO2 O3 divided by O2. Now we have something that we can compare out there. We can compare this guy to. Do they match now? The answer is yes, they do match, right? Because up on top, if I wrote this correctly, that should be O3 for both of those. That would be better if I could actually copy that better. That would be O3 squared divided by O2 in that case. And something to the -1 is 1 over it, right? So that basically is the exact same. So they actually do match if you use the correct subscript there when you copy it back over. So yep, they do match. So it does match, and it is a plausible mechanism. Yeah. Any questions on that there? All right, we will lay it up there for